Ladies and gentlemen, welcome to the Big Bear Math channel. As we're revving up for the AP Calculus exam, we're in 2018 BC. Question number 4. It is a non-calculator question. There's going to be a couple moments in this problem where you maybe wish you had that calculator in your hands, but we'll grind through it. We'll get through it. This is you're going to see a classic tabular question with some nice little twists in it along the way. And this is kind of what I consider a happy medium type of question. It's not the easiest one we've seen all year, but it's going to be very doable, I think. So let's take a look here and see if we can dive into this, Bear. So here we go. We're describing the height of a tree by this h of t function right here. It's measured in meters, and t is measured in years. And different selected values of h are given above. And what you'll notice is that the gap from like 2 to 3 is 1 year, but from 3 to 5 is 2 years. So we have what we call unequal subintervals. Okay, worth noting. So right out of the gates, we want to estimate h prime of 6. And then don't let me forget, we got to write a sentence to interpret the meaning of h prime of 6 in the context of this problem. That's great practice. It's already the second time that same question's come up on this particular year's exam, and we're definitely going to see it. So let's see if we can estimate. Basically, what we're saying is the slope between these 2 points right here, which that would be a secant line, is going to be roughly approximate to the slope of the tangent line at t equals 6. So that's what you're going to see us try to do here. So we'll move over to a nice blank page here. And let's see if we can write this out. Again, in a nutshell, just so you can see where the setup is going to come from, we've got this h function. Here's t equals 5. Here's t equals 7. The slope that connects those 2 points is almost going to be, very, very close to being parallel to the tangent line at 6. There's certainly no guarantee that they will be exactly parallel, but that's why we call it an approximation. So we're going to say that the slope or the derivative's value at 6 is approximately h of 7 minus h of 5 all over 7 minus 5. Now, reading that table that we had there in front of us, and I'm going to leave a link below here so that you can open up your own page with this question. It looks like it's going to, h of 7 was 11 and h of 5 was 6. 7 minus 5 makes 2. So when I'm all said and done, I'm getting 5 halves. Now, what are the units on that, Bear? Well, the 11 minus the 6, these values were meters. 7 minus 5, those were years. So at the end of the day, this is going to be meters per year. All right, now we want to try to write a sentence. Okay, generically speaking, if I just saw h prime of 6 and I hadn't read the question, I didn't know the context, I would have said h prime of 6 is the rate at which the function h is changing. And there's nothing false about that statement, but it lacks a few key elements that we need to have to get full credit. And I'm going to say there's 3 things that I want to incorporate. Number 1, I've got to do a more specific job of describing function h within the context of the question. Number 2, I want to include the specific moment t equals 6. And number 3, I want to include my units. So let's see if we can improve and spice this up a little bit. I'm going to try to talk through this as I type here at, we'll say at time t equals 6 years. Okay, so there's my specificity that we referred to. Now I want to try to describe function h using their terminology. And I'm not going to, reinvent the wheel here. I'm just going to steal some of their verbiage. I'm going to say the height of the tree. Okay, there's my function h. Now I need to address the fact that it's a derivative. There's a prime sign, okay, is changing at a rate. So there's my prime sign. Now my answer was changing at a rate, I should say approximately. Rate of approximately, we'll say 5 halves. And then my units are going to be meters per year. And now I've covered all my bases. So really spent a little more time than I planned on in part A, but I just want to really make sure we feel good about that question. Now, part B here, explain why there must be at least one time, and you're already starting to feel like some type of existence theorem. The theorems that are big in our course are the intermediate value theorem and the mean value theorem, as well as, I guess we could say, the extreme value theorem as well, but it's certainly less common. We want to see, is there ever a moment where we could guarantee that the derivative of h is going to be equal to 2? And I can't stress this enough. If we're going to use data from h of t to prove the existence of an h prime value, we are using the mean value theorem every time. And so now the challenge is we got to do a lot of kind of mental calculations. And so I'm going to do like, what if I calculated the slope from 2 to 10? No, that's not going to be 2. It's going to, I'm already seeing it's going to be some kind of decimal thing maybe. What if I did the slope from 2 to 3, 3 to 5, 5 to 7, 3 to 10, 5 to 10, 7 to 10? There's a lot of combinations in there that you kind of have to exhaust. But the one that I eventually did kind of catch my eye was this 3 to 5 interval right here. And as you evaluate the slope between these 2 points, I think you're going to get a 2. And so let's walk through how we're going to justify this question using the mean value theorem, because there are a few hoops we want to make sure we jump through. So again, for emphasis here, if we're using data from h of t to prove the existence of an h prime of t value, we're using the mean value theorem. Now, there is a situation where if you were using data from h to prove the existence of another h value, and it was an h prime right here, then we'd be using the intermediate value theorem. Now, the first thing that I want to kind of check off here or try to prove or verify is that the slope between t equals 3 and t equals 5 really is 2. So I'm going to say h of 5 minus h of 3 over 5 minus 3 turns out to be, let's see, 6 minus 2 makes 4, divided by 2 makes 2. And again, we might as well include units for fun here. Okay, now the next thing we're going to do, so what are the prerequisites? Like, this theorem isn't even really applicable or guaranteed to be true unless a couple of things happen to be true. So we could say, well, first of all, because or since h prime, and this is all in the original opening paragraph, since h prime is differentiable on the closed interval, we'll say from 2 to 10. And you could be more specific. We could use 3 to 5. You can always use a more broad interval. You just can't use too small of an interval. Then h of t must be continuous on the open interval. And I could have said closed right there in that moment, but I can't say, but I couldn't use open when I'm describing differentiable, if that makes sense. 2 to 10, okay. Then by the mean value theorem, here's my favorite part, must exist a t, and we'll say 3 is less than that t, which is less than 5, so we're kind of sandwiching it in, such that h prime of t equals 2. Boom! And there's everything you need about the mean value theorem. Hopefully I didn't go through that too fast. If you do, we've got some other videos that go a little more in depth into that mean value theorem and give you more chance to practice that justification. Usually the mean value theorem is either one of your best friends or your worst enemies. And with just a little bit of practice, I think it'll be your best friend. So part C says, okay, we're going to use a trapezoidal sum. Love it. That's going to be used to approximate the average height of the tree. Now, the average height of the tree is like saying, hey, let's find the average value of this h of t function here, okay? And what we're going to do with our trapezoids is, I'm kind of thinking it's the formula for a trapezoid is going to be basically the average of the two heights multiplied by the base of that trapezoid. So my first trapezoid here, the heights are going to be 1.5 and 2. So I'm going to add those together. And then I'm going to multiply their average by the width of the base, which is the width between the 2 and the 3. So this base is going to be a 1. But you'll notice as we go through, the bases do change. From 3 to 5, the base is going to be 2. From 5 to 7, the base is going to be 2. from 7 to 10, the base is going to be 3. So don't assume that those bases are always going to be the same. All right. So again, I'm going to jump off of this page so that you may not be able to see the table anymore, or you can just pause right now, try to set yours up, and then come back and hit play and see if we set ours up the same way. So here's what my setup's going to look like. Again, we're using the average value formula, so to speak, which is 1 over b minus a times the integral from a to b of whatever function it is you're trying to find the average of. So specifically to this question, we've got a coefficient of what's going to become 1/8 times the value of that definite integral, and we're approximating the value of that integral using a trapezoidal sum, okay? So everything inside of these square brackets is what I believe to be my trapezoids. I've got my first trapezoid plus my second trapezoid plus the area of my third plus the area of my fourth. And again, these are my heights. Here's my base, height 1 plus height 2 times that base, height 1 plus height 2 times his base, et cetera, et cetera. Now, and we're just going to cut to the chase. This is probably one of those real annoying moments where you're like, geez, I wish I had my calculator. But no such luck. So you got to kind of grind through it. I don't think you'd be enrolled in this class if you weren't capable of that. So I know you can do it. Just for checking your answers, I got 263 over 32, and that's going to be meters. So that's the average number of meters of the height of the tree from year 2 to year 10. All right, we're coming down the home stretch here. We're into part D, and this is very, very common with tabular questions where they're going to magically at some point in the question kind of ditch to the table and say, you know what, the height of the tree can also be modeled by this particular function right here. So we're replacing the table. We're done with the table, and we're replacing it with g of x. Now, x, the input, is the diameter of the base of the tree in meters, okay? And then the output values are going to be the heights. So input is diameter, output is height. Now, there's a particular moment when the tree is 50 feet tall. Now, that's its height. That's going to be an output value, so to speak. That's a input and output are terms I like to use for the independent variable and the dependent value and things like that. So anyway, there's a moment where the tree is 50 feet tall, and at that particular moment, the base, okay, which is your x value, is increasing at a rate. So that's telling you now we're describing the derivative of x. So I'm thinking to myself, dx dt is going to be 0.03 meters per year. According to this model, what is the rate? Again, we're thinking derivative of the change of the height of the tree. Height's measured by g, so I need the derivative of g with respect to time in meters per year. Okay, now this is a really big deal because g is in terms of x, but we're going to be deriving it with respect to t, so we need to practice or exercise kind of our implicit differentiation rules. So in a nutshell, we're going to derive this function with respect to t, and then we're going to plug in a 0.03 for the dx dt. And I think, spoiler alert, we're going to address this right now. We actually don't know what x is when the tree is 50 feet tall. So I'm going to substitute the 50 for g. I'm going to cross multiply that and solve for x. So if we said 50 equals 100x, I was kind of going to hold off on this and see, after we got, the derivative taken care of, if we caught that. A common mistake is substituting the 50 itself in for x. But again, x is the diameter, and 50 in this case is not the diameter of that tree. That'd be one big tree. So cross multiply, I get 50 plus 50x equals 100x. Subtract 50x over, divide by 50, you'll get x equals 1. So at this particular moment, the diameter is only 1 meter. All right, so here we go. We've got our g of x function. I want to derive it with respect to t. The first thing I notice out of the gates here is that I want to use my quotient rule. So I'm thinking low d high minus high d low. All right, low times the derivative of the higher part, which is in this case, normally I would just say 100 is the derivative of 100x. But again, because it's with respect to t, I'm going to say 100 times dx dt minus the high times the derivative of the low. Again, normally that would be 1, but in this case, it's dx dt. All right, all over the low squared. Now what we need to do is we want to measure the derivative, or you could use this notation here. You could say the derivative of g with respect to t evaluated at, I'm going to say x equals 1 meter. So let's see, 1 plus 1 makes 2, 100 now multiplied by 0.03 makes 3, 100 times 1, and 0.03 again for dx dt. All over 1 plus 1 makes 2 squared, 4. Okay, so we're going to get 6 minus 3 over 4, 3/4. Again, that's a rate, so this is going to be meters per year. And that's how fast the tree is going at the instantaneous moment where the diameter has a base of 1. So that's a wrap, ladies and gentlemen. Hope that helped. If this helped, please hit subscribe below, share your comments, share this video with some friends, and help spread this, spread these videos, because all we're trying to do is get you ready for that AP exam, get you a little closer to your dream score of a 5. I know you can do it. We're going to go get that 5. And all right, have a great night.